What do you call a sphere with an infinite radius? A hyperplane that's having an identity crisis. My name is Pavlo Melnik. I'm a PhD candidate at Computer Vision Laboratory, Linköping University, Sweden. I will now present our TetraSphere paper, proposing a neural descriptor for O3 invariant point cloud analysis. We consider geometric learning on 3D point clouds with neural networks. Two requirements for such a task in natural science applications are permutation and 3D rotation reflection, that is O3 equivariance. At the same time, models making invariant predictions eliminate the need for data augmentation. Our paper presents TetraSphere, a model for point cloud analysis based on equivariant steerable 3D spherical neurons and 4D vector neurons from prior work. Here, we use the steerable spherical neurons in an end-to-end learning pipeline for the first time. A quick recap of prior work. We have previously argued that spheres are a more natural alternative for learning in the Euclidean space, and proposed a model based on spherical decision surfaces, which has extended geometric modeling and interpretability. A spherical neuron is defined as a neuron with a spherical decision surface, obtained by means of the conformal embedding of a Euclidean space in Minkowski space. In practice, this is a nonlinear embedding of the input, where one simply appends two scalar values to the input vector. Then, through specific normalization, one can interpret the learned parameters as hyperspheres. We assume that the gamma equals 1 for the rest of the background recap. Spherical neuron activations are nonlinear with respect to the original input, thanks to the embedding. Moreover, the activations are isometries in the Euclidean space. Plainly speaking, it means that rotating the neuron produces the same effect as rotating the input. The follow-up work investigated this isometry property in the context of 3D rotation equivariance, where we proposed steerable 3D spherical neurons. To construct these neurons, we copy a single learnable spherical decision surface such that the resulting four spheres are spaced in 3 dimensions equally to form a regular tetrahedron. We note that this neuron produces a 4D vector output, unlike the simple spherical neuron that produces a scalar output. In the current paper, we further demonstrate the utility of the steerable 3D spherical neurons by using them as the key element of our O3 invariant model. We propose to use them in combination with vector neurons. In the proposed TetraSphere, the input point cloud first propagates through the O3 equivariant TetraTransform layer, consisting of k steerable 3D spherical neurons, that lifts the input 3D points to equivariant 4D representations. We then apply equivariant pooling to this output based on the L2 norms, thus selecting only one steerable neuron output out of k, the one that has the most of the activations with largest norms. To learn deeper equivariant features, we use vector neurons, adapted for operating on our equivariant 4D features. For this, we use the VN-DGCNN from prior work, now with dimension 4. Evaluated on randomly rotated shapes from the ScanObjectNN dataset containing real-world object scans with occlusions, noise, background, etc., TetraSphere achieves state-of-the-art performance. The performance in the synthetic ModelNet 40 classification and ShapeNet part segmentation tasks is the highest among competing equivariant methods, and decent overall. The parameter difference between TetraSphere and the baseline VN-DGCNN is negligible. TetraSphere has only 5 more parameters. With such a minuscule difference, it achieves superior performance in all the experiments. The time complexity difference between the two is adequate and comes from the usage of 4D vectors by TetraSphere and partially from the TetraTransform operations. We can easily interpret the key learnable parameters of TetraSphere. They are literally spheres. Here we illustrate how they change after training the model end-to-end. As we can see from the figure, TetraSphere learns all but one gamma parameter of the spherical decision surface defining the steerable neuron to be close to 0, effectively always selecting one steerable neuron out of k. Training the model with k greater than 1 in most cases results in higher performance, which we attribute to a higher chance of selecting a better initialization of the steerable neuron parameters. We look forward to our work paving the path to more geometrically justified handling of real-world 3D data. Consider taking a closer look at our paper and code. Feel free to check our other papers in the series. Thank you.